6.2, we're talking about power functions. I have mentioned these before in class because they are just powers of x. So x is a power function, x squared is a power function, x cubed is a power function, x to the fourth is a power function. We call these monomials because there's only one polynomial term. So there's one term in the whole function and it's a polynomial. The general form is c times x to the p, where p is just some constant. So x, x squared, x cubed, and so forth. Examples with a constant would be like 4x squared. That is a monomial or a power function. 3x cubed, negative 2x. There's just a constant and a power of x in all of those. These are particularly useful because we know what their graphs look like, and so if we combine this section with 6.1, where we're adding functions together, we can construct what a polynomial looks like that has multiple terms from its composite pieces. So if you have an even power of x, the general form of it is like a parabola. It's very similar to a parabola. If you have an odd power, it looks more like an x cubed that just gets steeper and steeper with higher powers. So higher powers will have a steeper curve on values of x that are greater than 1. I have sketched in here various x, so starting with x, just as your line, which you're used to, then you have x squared in there, that is the widest of the parabola shapes on the outside, but more narrow on the inside, and that's what I'm talking about with this value of x greater than 1. They all pass through 1, 1, and then the odd powers pass through -1, -1, and the even powers pass through -1, 1. In each of these cases. So x squared, x cubed is in red, x to the fourth is in brown, x to the fifth is in gray, x to the sixth is in orange. And I just sketched them all in there so you could kind of see that as the power gets larger, the graph gets steeper on those bigger values, but it also gets sort of more and more square shaped on the bottom, down here where you can see where its curve is between 0 and 1, it gets smaller because if I take a small number and I multiply it by itself a bunch of times, it's going to get closer and closer to 0. A brief comparison with power functions and exponential functions, because you're not really used to seeing how those compare. We compared linear with exponential, but not power. So I've taken 3 to the x and x cubed, and I sketched out some data points here. You can see that they are the same when x is equal to 3, because 3 cubed and 3 cubed, you're going to get the same value. And then I sketched them here. So you can see x cubed has that general shape that we were talking about where it's negative on the negative side, positive on the positive side. Obviously exponentials are never negative, so there's one distinct difference. Also, even though the graphs touch at 327, x cubed is still wider. It does not grow as rapidly as the exponential function, just so that you know that. Your exponential is always going to grow faster because it's a base raised to a power, and that power is increasing as opposed to the base increasing, which is what's happening with x cubed. The base increases, but the power is the same, and the power is going to cause it to grow much more rapidly than the base in this case. I mentioned that the nice thing about the power functions and combined with the previous section is that it allows us to construct polynomials. Another thing here is that your transformations that you did the lab on are key, because transformations are exactly what we're doing to these power functions when we construct general polynomials. So once you know the shape of your general power function graph for any power function, you can add transformations to that graph that just change the shape. Here I did one of the more simple examples. I took x minus 2 squared and then added 1, so that's shifting right 2 and shifting up 1, just to give you an example to remind you of what you did back in chapter 5. So this is a transformed version of x squared, and then I sketched in the graph of x squared and the transformed graph. So you can just see visually what I'm talking about. That's something that you will want to get confident in. Those same transformations work exactly the same way with our power functions as they did with our earlier examples. Direct proportionality is something that we talked about before, but we only talked about it in the context of directly proportional to x, not in terms of power functions. Again, you can have a direct proportionality with a power function. Your area for a circle, right, which we talked about quite a bit earlier, a pi r squared, the area is directly proportional to the square of the radius, right? A is proportional to r squared. It's not proportional to r, but it is directly proportional to r squared, and it has a proportionality constant of pi. So the same concept you did before, but now with respect to a power function. This is also where we first explicitly talk about fractional powers, which we have talked about in class actually quite a bit, but your fractional powers, as you probably recall from that discussion, it corresponds to a root function. So if I have x to the m over n, I'm taking the nth root of x to the m. That's what that corresponds with. So x to the 3/2 is the square root of x cubed. X to the 8/6 is the 6th root of x to the 8th, which I could reduce to x to the 4/3, but which would be a cube root of x to the 4th, but right, you get the idea. Whatever is in the denominator of the fractional power is the root that corresponds to that function, which allows us to then talk about modeling with power functions. So if I give you an example like stopping distance, which is directly proportional to the square of the speed, so that says that d is proportional to s squared, then the equation in this particular case would be d equals 1/30 times s squared, where s is in miles per hour and d is in miles. First, let's find an inverse function, right? We did this again in chapter 5 for the speed in terms of the distance. So because this is a physical problem, we aren't going to be talking about negative speed or negative distance. We will consider that both are positive, which means I can take a square root, and it can be an inverse function because it's only the positive of the square root and not the negative, since I know I won't have negative speed. So I can solve for s in the equation. So 30d is equal to s squared. I take a square root of both sides to get that the square root of 30d is equal to s, assuming that there are no negative speeds. Interpret this equation. What does that mean? Well, it's saying that the speed is directly proportional to the square root of this stopping distance. So, if I have a car that takes half of a mile to stop, how fast was it moving, given that equation? So then I would just substitute in half a mile as my stopping distance. So the speed would be the square root of 30 times 1/2, or square root of 15, which is about 3.873 miles per hour. So only about 4 miles an hour, but it took half of a mile to stop. That seems pretty conservative of an estimate for how long it would take to stop, but it's a useful measurement anyway. So please let me know if you have any questions.